In this section, we're going to be focusing on this idea of continuity, which might be something that you've seen in a previous math class, but if you haven't, that's okay. We're going to review it, and then we're going to give a more precise definition of continuity because we're going to use our idea of limits here. So first, we're going to talk about continuity over an interval. It says a function is continuous over an interval if its graph can be drawn without lifting a pencil from the paper over that interval. So if you're drawing your function or you're sketching your function and at no point do you have to pick up your pencil from the paper, we would say that that function is continuous. Any point where you do have to pick up your pencil from the paper, so if I have like a hole in my graph or if I have a break or something like that, I would say that this x value right here is the location of a discontinuity, or we might say that f of x is discontinuous at that particular x value. So first thing I want to do is just kind of address the different types of continuity or discontinuities, that we'll see in our class. So first of all, a function that's continuous everywhere, these are probably the majority of the functions you've dealt with in the past. It turns out that all polynomials are continuous everywhere. So if you take a line, a quadratic, a cubic function, anything like that, that's going to be continuous everywhere. And in general, we like it when things are continuous. When functions are continuous, they're easier to work with, and we can do more cool calculus stuff with them. So functions that are continuous everywhere, you would probably look at that function and not even really think about continuity. You would just say, oh, that's a parabola. A hole in the graph could be a discontinuity. So if I take even just that same function, right, if I take a parabola and I put a hole in the graph, I have a discontinuity right here at this particular x value. If you want to impress your friends, this is also called a removable discontinuity. So if you just want to sound smart, you can say removable discontinuity, but otherwise we'll just call it a hole in our graph. A jump discontinuity, so this is going to be when your function jumps up or down. So if I have a big jump at a particular x value from one point to another. So here at this particular x value, I have my discontinuity. These are most common in piecewise defined functions. So that's where you're going to see this occur most of the time. And I think, as we'll start to see, usually the discontinuities, your eye is naturally drawn to discontinuities because it's kind of something out of the ordinary. You're like, wait, what's going on there? Something different's happening. So I think usually it's easier to pick out where a function is discontinuous to think about where it's continuous. And then finally, we have asymptotes, and I should specify here that we're talking about vertical asymptotes in particular, vertical asymptotes. Here, if I have a function that has a vertical asymptote, we might have something that looks like this. Horizontal asymptotes will not cause discontinuities. So it's really vertical asymptotes. Those are the ones that we're going to be worried about. And then right here, obviously, right here, there's a really big problem, right? You have to pick up your pencil at that point, so that's going to be a discontinuity. Jump discontinuities and vertical asymptotes, those are, again, if you want to impress your friends with how smart you sound, those are called non-removable discontinuities, which isn't anything you need to know. It's just kind of a fun fact. So one thing that I will be asking you to do here is I'll give you the graph of a function and I'll say, okay, go and tell me where this function is or is not continuous. And I think usually identifying the discontinuities, so identifying, oh, there's a hole right here, or there's a jump right here, or there's a big, huge vertical asymptote right here. Those are usually easier to pick out, but then you also want to be able to identify why that function is not continuous there. And for that, we need a more precise definition. So now we're going to talk about continuity at a point. So it says a function f is continuous at a point x equals c. So here c is just a stand-in for any number. If, first of all, limit as x approaches c of f of x exists. So the limit has to exist at that x value. f of c exists, so the function has to exist at that particular x value, and then the limit at that x value of our function should be equal to the value of the function. So here we're just saying, okay, the limit needs to exist, the function needs to exist, and then number 3 is saying, okay, those two things need to be equal. And if any one of these 3 fail, f is discontinuous. So if you look at step 1 and you say, okay, the limit does not exist, you can just stop right there. You don't need to check the other 2 that are on your list here. In order to be continuous, you need to meet all 3 of these criteria. So here is an example of a function. I might say, okay, let's go talk about the continuity of this function at various x values. Or I might say, oh, go tell me where this function is continuous. Identify the discontinuity. So here we're just going to talk about these different x values. First, I have x equals -3. And really what I want to do is I want to, first of all, determine whether it's continuous or discontinuous. And then if it's discontinuous, I want to talk about why. If it's continuous, we'll actually go and show that it is continuous there. So for number 1, x equals -3. So we're talking about this x value right here. And I see, hopefully you'll recognize that we have a hole in our graph right here. So if you recognize that, you can tell me right away that this function is discontinuous. But then I also want you to be able to tell me why. Tell me why this function is discontinuous. And if you're not sure why, we're checking one of these 3 properties here. Now, if you can recognize it, you can just tell me, oh, it fails this property because blank. Or the other thing you can do is you can sort of treat this like a little checklist here, right? So I can say property number 1, does the limit exist? Well, the limit as x approaches -3 of my function f of x. What does that look like? So as I approach -3, it looks like I'm approaching this hole from both sides. It looks like that hole has a y value of 1. So we would say, okay, that limit is equal to 1. So, okay, the first criterion is met. Second, does f of c exist? Well, I have a hole in my graph right here, which seems to be a big problem, and I don't have another closed point at x equals -3 to kind of compensate for that hole. So in this case, we would say, well, it's because f of -3 does not exist. So this is really why. This is what I would be looking for if I asked you to justify your answer. If I said, okay, tell me why this function is discontinuous. Well, it's discontinuous because f of -3 does not exist. So let's talk about 2. Next, we're going to talk about x equals -1. So here I want to look at x equals -1. Again, we want to say, okay, here's x equals -1. What's going on right there? Well, if you look back at the types of discontinuities, you could probably see, oh, that is going to be a jump discontinuity, or a break in the graph, we might say. So it's discontinuous there, and I want to determine, okay, why is it discontinuous? Which of these 3 criterion does it fail over here? What's kind of falling apart right there? So again, if you need to, you can just work your way through that checklist. So I'm going to check number 1. What's the limit as x approaches -1 of f of x? Well, here in this case, as I approach -1 from the left-hand side, it looks like I'm approaching a y value of -1. And as I approach -1 from the right-hand side, it looks like I'm approaching a y value of 3. Here in this case, the left-hand limit and the right-hand limit are not the same, so we would say that the two-sided limit then does not exist. So the limit does not exist. That's all I need to show then at this point. The limit does not exist. I don't need to check any of the other 3. As soon as you find that first part that's not true, the rest of this definition sort of falls apart here. We don't even need to bother checking the rest. All right, so let's talk about what's next. X equals 2. So 3 right here. We're going to talk about x equals 2 right here. So, okay, you might look at that and say, well, maybe you're not quite sure what's going on there at x equals 2. It looks like it's probably going to be a discontinuity, but let's actually go and show why that is the case. So I'm just going to work my way through this checklist here. So the first one says, does a limit exist? Well, what's the limit as x approaches 2 of f of x? So here, as I approach 2 from both the left and the right hand side, I'm approaching that hole. That hole has a y value of, it looks like, positive 3. So okay, the limit exists. That's not a problem. 2, okay, what is f of 2? When I take 2, plug it in my function. So here, I'm not looking at this hole right here, right, because my function doesn't exist. I'm looking at this closed circle down here at x equals 2. So at x equals 2, that has a y value of positive 1. So okay, the function exists. So the limit exists, the function exists, but as we'll see in number 3, right, hey, look at are these two things equal, right? 3 is definitely not equal to 1 the last time I checked. So this is why our function is discontinuous. So our function is discontinuous at x equals 2. Whoops, and I forgot to label that back here too, right? For x equals negative 1, our function is discontinuous. Lastly, then, we want to talk about x equals 4. Let me erase these just so that we, don't get distracted. Okay, now we want to talk about x equals 4. So, we're kind of running out of room. Let's erase this guy up here. So x equals 4 is kind of a different case. Something you might look at that and say, well, I don't really know what's going on there. So let's talk about that. X equals 4. So we're talking about this particular x value right here. It looks to me like it's continuous. I think that this function is continuous, but let's go and check. Let's make sure. So first thing we need to check, what's the limit as x approaches 4 of f of x? Well, as we approach 4 from the left-hand side, looks like we're approaching the x-axis, which has a y value of 0. And as we approach from the right-hand side here, it looks like, again, we're approaching the x-axis, has a y value of 0. So here it looks like my limit is equal to 0. 2, the function, what is f of 4 here? So f of 4, there's no... let me erase these so we can get a better picture. There's no holes or anything in our graph. We're just looking at this point right here. Well, that point has a y value of 0. So, okay, the limit is 0. The function is 0. Number 3, 0, in fact, does equal 0. So this function is continuous at x equals 4. So on a quiz or an exam, I might say, okay, here's the graph of a function. First of all, tell me, is our function continuous there? And then if it is, also tell me why. So I would have this definition of continuity at a point memorized. This is a definition that I often like to ask about on, say, an exam. So I think it would be a good one to study. I would know that definition. I'll try and point out definitions that I think are worth knowing really, really well or memorizing. Of course, I think they're all important, but I'll tell you the ones that I'm going to be asking you about on quizzes and exams. So let's look at one more quick example before you wrap this video up. Here, I've got 3 different functions, and I'm just going to use the graphs of these functions to discuss its continuity here. So a couple of these, I've gone ahead and given you the graphs, but I want to discuss these graphs because they might be a little bit misleading, and in particular, it's part A that's really going to give us a lot of issues here. If we look at part A, x squared minus 1 over x minus 1, and we actually have just the equation of a line right there. So this one is perhaps a little bit, maybe you're not quite sure about that, and rightfully so. if you were to graph this on say a graphing calculator, this is exactly what you would get, and it might be difficult to determine the continuity. I might take this and I might say, okay, well, let's look at this equation just a little bit closer. X squared minus 1, I know that's x plus 1 times x minus 1 divided by x minus 1. I know I can cancel out that common factor. Well, what do we know from the last section? We know that if I take that factor, x minus 1, set it equal to 0, and solve, that means I have a whole at x equals 1. So technology, again, I just wanted to do this to show, hey, technology does not do a very good job of displaying holes in our graph or telling us whether a function does or does not exist at one specific x value. When it comes to quizzes and exams, I will be sure to, I won't ask you any trick questions like this. I will make sure that if I give you the graph of a function, it shows any holes in the graph or anything like that. So this function now, if I look at this, think about tracing this function, where do we need to pick our pencil up? Sometimes it's easier to locate the points of discontinuity rather than to think about where a function is continuous. So here, if I were to trace this function, right, as soon as I get to that hole, I know I'm going to have a problem right there. That's a discontinuity. But then everywhere else, it looks like it's fine. So you could talk about the continuity of this function in a few different ways. The way I would prefer that you talk about the continuity here is to use interval notation. So really what I want to do is I want to say that this function is, you could say, well, it's continuous. I can spell continuous at all x except x equals 1, right? Because that's the location of our hole. And you would be correct. And I would say, yep, you got that question right. But what I want us to start doing is to practice using interval notation. It's something that we're going to be using a lot of in this course. So I want us to start feeling comfortable with it as early as possible so that when we get to more complex ideas, we don't need to revisit this idea of interval notation. So here what I would say, instead of saying that, I would say that this function is continuous on, and I would give these intervals. So where is it continuous? Well, it's continuous everywhere except 1. I want to say that this function is continuous everywhere except for 1. So it's continuous over here on the left-hand side of 1. So I would say, okay, it's continuous starting way over here on the left-hand side, starting at, say, negative infinity to 1. Now I want to say that this function is not continuous at 1. So the way I'm going to do that is I'm going to use parentheses here around 1. If you used a closed bracket, you would be telling me that the function is continuous at 1. So we're going to put parentheses around 1 here. And then I think our book uses union in between intervals. You could use a comma here instead. I'm going to use a union just to be consistent with what our textbook uses, because we also have this area over here. We also have this area over here to the right of 1 we need to talk about. So all of those numbers to the right of 1, we're starting at positive 1 and we're working our way towards, well, positive infinity, and it's continuous on this interval here. So this is the way I would write it. If you want to put a comma, and I can't remember which our textbook uses or what my math lab will use. I believe they use union though. So if you happen to put in an answer and it marks it wrong because you used a comma instead of a union, please feel free to email me. I'm not going to ask you to do that question again. I can just go in, see your answer, and give you credit for it, because that's notation here in this case is not something that I am going to be particularly picky about. So there is our answer. It's continuous on negative infinity to positive 1 and positive 1 to positive infinity. Next up, we've got square root of x. And again, here I've got this function. Well, okay, over here it really looks like it's no problem. It looks like over there it's going to be fine. But really it's the behavior right here at 0 that perhaps I'm not quite sure on. This graph didn't really do a great job of displaying it. And if you're not sure, just think about, well, what does our function exist there? Does it exist? Can I take the square root of 0? So I'm actually just going to plug that in. So square root of 0 is just 0. So that tells me I know that I have a point right here. I know my function exists right there at 0. So I know my function is continuous everywhere to the right of 0. So I might say, okay, my function is continuous on 0 to positive infinity, because we're talking about the x values here. Now, positive and negative infinity, we're always going to be using parentheses around those every single time. 0, on the other hand, we need to decide, well, is our function continuous at 0 or not? Here, we are going to be a little bit, I don't want to get too lost in the details here, but we're going to say, yes, this function is continuous at 0. There's this idea of left continuous and right continuous. We would say that this function is continuous from the right here. I don't want you to get lost in definitions here. I don't want to get too into the weeds. But you could tell me, hey, this function is continuous at x equals 0 because the function exists there at x equals 0. The limit from the right-hand side exists, and the function simply does not exist on the left-hand side. So we would say, okay, yes, it's continuous on 0 to positive infinity, 0 included. Lastly, C, I have y equals the cubed root of x. And this one here, I'll tell you, there is no real trick to this. What you see is what you get. So if I was drawing this function, I'm not going to have any holes or breaks or anything like that in this graph. This function simply, to me, looks like it's continuous everywhere. So, if I'm tracing this function, or if I'm drawing the graph of this function, there's no place where I need to pick up my pencil from the paper. I just can draw it right on there. So if it's continuous everywhere, I would say, well, this function is continuous from negative infinity to positive infinity. That's the way for me to say, you know what, it's continuous for all real numbers. So please keep these last two in mind in particular. We're actually going to be revisiting this idea in the next video, because we're going to start to talk about, okay, if we don't have the graphs of functions, how can we determine continuity algebraically? And it turns out roots are going to be kind of one of the trickier ones to consider. So we'll talk about that in the next video.